Hello everyone, welcome to another video. I've received requests to go over a problem such as this, a kinematics problem, in class, so we are going to do that. So if you look at the problem says you are a track and field runner getting ready for a race. The track is a 100-meter dash, and so your goal is to reach your top speed in the first 20 meters and then maintain that speed for the last 80 meters. You know that your best acceleration is 1.6 meters per second, or meters per second squared. How long is it going to take you to run the 100-meter dash? It is at this point that I would like for you to please stop the video, pause, try and solve this problem yourself before we move on and continue the problem. Okay, so pause the video, try it for yourself. So the first thing you want to do when you're doing a problem like this is always draw a picture, okay? So we're going to draw a picture. Alright, so here's our picture. I included the acceleration of 1.6 meters per second squared, excuse me. We have the track. Here's the first 20 meters where you will be accelerating. Here's the second 80 meters where you will be traveling at a constant velocity. You are at the 0 point. I consider this direction to be positive, this direction to be negative, which we'll put over here. This is a complete picture, okay? The next step, just to make sure you understand what direction acceleration and velocity are, I'm going to draw a quick motion diagram. Okay, so here's our motion diagram. We have a change in velocity on this side, and then at the 20-meter mark, there is no change in velocity. Alright, so that essentially encompasses all the prep for the problem. Now we can start looking at the equations we need. So we have a few equations at our disposal. I will write them up here. Alright, so here's the equations we have to use, and what we need to do now is we need to look at the given values, look for what we're looking for, and then try and figure out which equation we need. Alright, so if we go through here, we see that we've got 100 meters, right? That's the total distance. For the first part of the problem, which is this part here, for the 20 meters, we know this, we know our acceleration, and we are looking for time, how long, okay? This, just because it doesn't say specifically what is the time, you have to sort of look for clues in the problem to figure out what you're looking for. And there's also here, there's maintain that speed, which means that you'll be running with a constant speed later. Alright, so we know we need time, we know we need distance, and technically, since we're starting from rest, we know we have a v initial of 0, so we have v initial. So if you look here, here's x final, x initial, v initial, acceleration, and t, right? So let's use this equation. So for the first part, part 1, we're going to be finding two time variables, right? This time 1 here and time 2 for here. So we write out our equation, all right, and we start plugging in the values that we know. So for our first part, we have x final, which is going to be 20 meters, if we consider this to be 0. So it's going to be 20 meters equals 0, plus our initial velocity, since we're starting from rest, is 0. Our acceleration we know is 1.6 meters per second squared. Alright, well, since this is 0 and this is 0, this entire part of the equation goes away, and all we're left with is this. Alright, this is what we're left with. So now we can start simplifying a little bit, multiply the two of these together, divide this to the other side, we end up with this, which gives us this. You'll notice the unit seconds squared. This is because I divided meters by meters per second squared. Since this is a fraction, you would multiply the reciprocal, which is seconds squared over meters. Meters cancel out, you're left with seconds squared, which is okay, because what we need to do now is we need to take the square root here, right? And so this gives us a time of 5 seconds. This time 1 is 5 seconds. Okay, so that's part 1. Part 2 is this part right here. But before we can do that and calculate that time, we need to know how fast he's going by the time, or you are going, I guess, by the time you get here. So we know our initial velocity to begin with here is 0. We know we are looking for a final velocity. We have our acceleration, and we have our time. So that would be this problem right here, right? We've got velocity initial, velocity final, acceleration, and time. So we plug in our values. Okay, and if you want to look at the units here, if you multiply seconds times meters per second squared, you're left with meters per second. And so this gives us a final velocity of 8 meters per second. Okay, so now we know that here he is running with a velocity of 8 meters per second. Now we can go ahead and calculate the rest of this time. You can use any number of methods to do this. I'm going to use, just to show you this one right here, using the big equation. Okay, so for this part of the problem, we know our x initial is going to be 20 because he's starting at 20. We know our x final is going to be 100. We know our initial velocity is going to be 8 meters per second. And our acceleration, since change in velocity is 0, our acceleration is going to be 0. So we end up with this. And so this whole part of the equation comes out, and we can solve for t, subtract 20 from this side, divide by 8. We end up with 80 meters over 8 meters per second is our time, which obviously gives us 10 seconds. And so this is going to be our t2. And so our total time for the race, time total, is equal to 5 seconds plus 10 seconds, which is obviously 15 seconds. Alright, so that is the total time for the race for this part of the problem. This is great and all. Now, let's make things a little more interesting. If you didn't understand how this worked, go back, read it again. If you did, let's move on to the next part. Okay, so it's race day, and everything is going as planned, but in the last 15 meters, you get a cramp and start to slow down with a magnitude of 1.6 meters per second. How long does it take you to finish the race? So now it is not exactly the same as before, because in the last 15 meters here, you now no longer are running with a constant velocity, but you are slowing down. Alright, which means that your delta v is going to be in the negative direction, which means you're going to have a negative acceleration here. So we need to now rework this problem. So instead of this being from 20 to 100, this is now 20 to 85. Because in the last 15 meters here, you're slowing down. So we can still use the first few parts of the problem. We can still use the fact that t1 is equal to 5 seconds. We have to rework the second part for t2, and we have to find t3. So to find t2, we can use the same speed. You're still moving at 8 meters per second, but this time you're only going at 8 meters per second from 20 to 85, so you're only doing that for 65 meters. So I'm going to use a different equation this time just to show you. We know that v is equal to delta x over delta t, right? So if you rework it a little bit, multiply both sides by delta t and divide by v, you end up with delta t is equal to delta x over v. Sorry for the writing. Which gives us our t2 now is equal to delta x, which is going to be 65 from 20 meters to 85 meters, and divided by our speed, or velocity, which is 8 meters per second, which gives us a time of 8.125 seconds for t2 this time. Alright, so now we have t2. Now we have to calculate t3. Once again, using our good handy position as a function of time for a constant acceleration equation. So we're going to be using this equation right here. Only this time, instead of our acceleration being positive, our acceleration is now pointing in the negative direction, since our delta v is pointing in the negative direction here. So we fill in our values. We get our x final is going to be 100 meters. Our x initial is going to be 85 meters, like we said. Plus our v initial we know is 8 meters per second, because that's how fast we were running before we started to slow down because of our cramp. 1/2, our acceleration is 1.6 meters per second squared, and t squared. Now, if you'll notice, this equation right here, our independent variable is t, right? And so we've got some coefficient t and t squared, making this a quadratic equation. Okay? which means that in order to solve for t, we have to do the quadratic formula. I'm going to cut ahead and do the quadratic formula, or write it out in its entirety. But if you need help on how to do this, please talk to me. Just remember that when doing it, this whole part right here is going to be your a, as in ax squared. This part here is going to be your b. And you needed to combine this to make this 0 to make this number c. So what you're going to end up with is something that looks like this. Okay, so you're going to end up with something like this. This negative 0.8 here is going to be our a, right? Negative b plus or minus the square root of b squared minus 4ac. Our a, which is this, is going to be 1/2 times negative 12.6, which is negative 0.8. That's why it's down here too. Our 15 is going to be 85 minus 100, which should actually be negative, excuse me. 85 minus 100 is going to be negative 15. That's our c, that's our a. Our b is obviously 8, hence negative 8 and 8 squared. And if we solve this, we end up with the following. 1.6. Now, you have to be careful here because you get two answers, plus or minus, right? The first answer we get is, if we add 4, we end up with 2.5. And if you subtract 4 and divide by 1.6, you end up with 7.5. And so the question is, which one is the right answer? Usually, depending on what your values are here, you may end up with a negative number. Obviously, that one is always the wrong answer. If you do happen to end up with two positive numbers, think of it this way. The graph for this right now looks something like this. Okay? Which means that when you get to 0 here and here, this is when you were slowing down originally, and this is when you turned around and came back. So if you were still moving with that acceleration after you stopped and turned around and came back, that 7.5 would be over here. So the time you want is actually this one. So now our total time is 5 seconds plus 8.125 seconds plus 2.5 seconds, which comes out to about 15.6 seconds. So you lost about 0.6 seconds because you got that cramp and were slowing down. Alright, I hope this helped. Please ask me any questions if you have it. This is sort of all the worst case scenarios with the exception of the timeless equation, which you guys got a lot of practice using in class. Good luck. Talk to you soon. Bye-bye.